It's off. It's off. What? Yeah, my mic is muted.
I don't know what kind of qualifiers you put on it, Nick, but anyway. So usually we used to go over memory management in 3100 embedded systems as a minimum, and usually you see it in operating system as well. But when I ask seniors, you know, how do you do with segmentation and paging in operating systems, and they come back and they say, why? So I have, working with the embedded systems groups over the past couple of semesters, it's dawned on me, actually it hit me like a brick. We need to pay more attention to it, because it's a very integral and important part of the hardware that you need to know in order to be a good programmer. The E is that's the hardware side of CSE, right? And the best programmers are the hardware that their software is good, without a doubt. So, without any further ado, you guys ready to roll? Okay. The Intel processors from the very early days, they had what's called the x86 architecture. And if you've had computer architecture, then I hope you're at least partially exposed to the x86 registers. Okay, if you haven't had computer architecture, don't worry about it. Okay, we'll explain a little bit. They had the Intel processors have a register set, of course, and we won't go into it for sake of time. But they originally used what was called for memory accesses. Intel used what was called real mode addressing. and I won't go into it too much, again, for sake of time, but a memory locations was referenced. It was specified by a segment register and what was called an offset register. Okay, and it was written that way. Okay, so for example, that's pretty much the edge, right? Okay, all right. So, for example, your code instructions were accessed by what was called the code segment register, and this kind of the students that have had me, especially for computer architecture embedded, I always refer to anthropomorphize a little bit. Memory is kind of like a huge neighborhood, right? What's in a neighborhood? Houses. And each house has a unique, specific address, correct? Right? So, in the memory system, which we call memory land, that's the name of the neighborhood. Thank you. It's called memory land. Okay, right? Each house is the same size. Each house can store a byte. Okay, we can put stuff into the house called writing. We can take stuff out of the house called reading. Okay, and it's not really reading is not really removing. It's just seeing what's in the house. Okay, so the memory location is the address in memory land. Okay, they're all the same size. So if we want more, a larger number, then we have to access multiple houses that are right next to each other. Okay, so the segment registers, and they still work this way, by the way, but in a heavily modified way. But the segment registers kind of point to a block in memory. Okay, and then we have the offset registers that say, well, the very beginning at offset is 0, and that's the house on the corner of the block. And then as we walk down the block, we have increasing offsets, increasing addresses, increasing offset register content. Go, Jacob. 100% yes. Yep. Which is why, I don't know if you've ever heard me say this, but the Postal Service should switch to hexadecimal addressing. It would really save a lot of grief. It really would. Anyway, so code segment kind of points to a block, right? And in the Intel world, the segment register has to be paired with a particular offset register. The code segment register in particular, because it's code, it's what you write and compile for high-level languages, assemble for some of them. Those locations are specified by the instruction. That's the offset register, okay? So the physical address in real mode, this is all real mode, guys. This is how the original 8086 processors worked. The physical address in memory land was specified by this one would be code segment times 10 hex plus the contents of the instruction point. When you add this, you get by the way, these are all 16-bit registers. When you do this, you get a 20-bit real address. And that's how original memory management worked. Go. It's a register. It's one of the 14. Originally there were 4 registers. So originally there were the code segment. We already know what that does, right? That stores the machine code, right? The stack segment, what does that do? Well, it points to the, which is really the top, but we won't go there. Okay. The data segment, what do you think that stores? Let me think, right? And because the guys at Intel, they kind of nailed it because this was devised about 50 years ago. Okay, this was started, maybe not 50, but 45. The design started about 45 years ago, and it's still used today, although it's been heavily modified. So the guys at Intel, they realized that for larger programs, you're probably going to need more data. So they have what's called the X. Okay, Jacob. Okay. And each one of these had its own little, not little, but its own set of offset registers that it could be used with. Okay. And this again was all real mode addressing. Okay. Now, since the physical addresses, guys, in real mode, this scheme produces a 20-bit real mode physical address. So that should tell you that the original address bus in the 8086 was a bit. The original 8086 had a 1 megabyte address because 2 to the 20th is 1 megabyte. Okay. Well, after several rather embarrassing quotes that became obsolete after a couple of months, okay, as the x86 line progressed, a couple years later, the 8186 came out, which really didn't do anything that the 8086 couldn't, so there wasn't a lot of market for it. The rumor on the internet is a lot of garage. But then, and that's about the only thing. The next advancement was the 286. And the 286 came out in 83-ish, I think. 1983, somewhere in there. The 8286 supported virtual memory. What's virtual memory? Go. I'm going to rephrase what you said, but you're right. You're right. You nailed it. Virtual memory looks like to the user/programmer that the entire hard drive is available as memory. How cool is that? They realized very quickly 1 meg ain't going to cut it. In fact, the 286, I think it went up to 24 meg main memory space. That still didn't cut it. So they said, you know what? We'll start putting these new things, 1985, new things called hard drives in these computers. And we'll pretend, we'll make a system of virtual memory that makes it look like the hard drive is the address space that's available to the programmer. Now, the average user doesn't know. Do they care? No. Yeah, as long as it does what you want it to do, good with me, right? Even as a programmer and engineer, okay, I'm fine with that. You're what? Oh. I see. I've never heard that word before in my life. Has anyone? If you say so, Nick. Along came the 386. 386, released in 1985, supports a whole lot of what we came out in 1985. Yeah. It supports 32-bit addressing. That means that in 1985, okay, when thumb drives weren't a thing, it supported a main memory system that was 4 gigabyte. Hard drives weren't 4 gig. You couldn't get unless you wanted to pay a lot of money, you couldn't get a 4 gig hard drive. So the hardware supported a main memory space that was larger than the hard drive that was in your average computer, okay? And then, of course, same thing over and over again, right? New things, cache, all that. Well, couple things that we can say that come out of real mode addressing that might not be totally obvious to you right now, but if we mention them, you should be able to envision, right? How big can a segment be in real mode? Well, the offset registers are 16-bit. So if you do the math, the segments are not from 0 to 64K, but they are all 64K, no matter what. Okay? They're fixed size. Well, how many of your programs use methods that are all fixed size, right? Programs that are all fixed size, arrays that are all fixed size, right? Not very many, correct? That was a huge disadvantage with segmentation. So what the operating system said, what they tried to do is they say, okay, fine. We'll be really careful with memory allocation, right? I can clobber this, can I not? So out there in memory land, what we have in real mode addressing and what they tried to do, because you also only have 16 segments if they're all 64K. That's just how the math works out. You only have 16 segments. So here's your 1 megabyte original, guys. 1 megabyte address space, all right? So they said, okay, here's code segment 1 or 0 index, okay? And it's, I don't know, it's say 4 kilobytes big. So then might have a little buffer, unused memory, right? Then we have a data segment. Maybe this is one, maybe it's 16K, right? And then we have the stack right here. The stack is sacred, right? You don't go screwing around with the processor stack. Right, Nick? The stack is sacred. Yes, you do. Thou shalt not corrupt the stack, right? Go. Oh, well, you're gonna learn that in linear. Okay, you're gonna learn that. A stack is a data structure. Okay, so it's a heavily used type of data structure. Hang on, Nick, I see you. Think of a stack of plates. Okay, so yeah, so a cafeteria, right? Cooks are dishing out plates right and left. Well, they're popping. It's called popping. They're removing plates off the top of the stack, right? So people eat, right? Turn their plates in. They go through the dishwasher, right? Well, where do those clean plates go? How can you? You'd have to lift the whole stack up. So it's called a last in, first out type of data structure, okay? So you push something on top of the stack. Later on, when you pop, that item that was last pushed on gets popped off. Does that make sense? It's the opposite of a queue. I don't know if queues yet. Yep. FIFO. First in, first out. That's called a FIFO structure. Does that make sense? Okay. So the stacks are incredibly important, and you see them all over the place. And you're gonna program them. You know, guys, you're gonna program them quite a bit. But those are programming stacks. There's something called the CPU stack, and that stores things like return addresses method. You go jacking with the stack, then when your method's done, you're not going to go back where you left off. You're going to go back to something else. Okay? Perfect.
Well, I'm playing that.
Some of the early and probably the current viruses exploited the stack. So they went in and they started altering the stack using malicious software. So when it returned, it didn't go back to your code. It went back to something controlling your bank account. Right? Bad. Okay. Does that make sense? Okay. So back to this, guys. So what they tried to do, and this could be in a space that is less than 64K. Do you see that? It could be. So technically it's all within the same segment, or at least it could be, right? But the operating systems tried to do it this way to save memory. What's the problem? You could easily have a problem where the data segment starts expanding into the stack segment if limits aren't placed on the index register, right? So you go to write a variable and you're starting to write stuff in the stack. Oh boy, that ain't good, right? So that didn't last very long, okay? So they went to what's called protected, and that's this selection. And I don't like to call this a lecture. I like to call this conversation. Okay? So we're, reverse. I guess we shouldn't call them lectures at all in any class, should we? Not really. Okay. So how does protected mode work? Well, I'm getting to it. No, we're good. So protected mode gives us a few features. Let's talk about the features, then we'll show how it works. So protected mode is a scheme where the segment register points to a beginning address, starting address. We'll call it a base address because that's what it is called. In what's called a descriptor. Descriptor table lies in main memory. Okay. So the segment register, it doesn't do this at all anymore. Okay. It points to a descriptor in a descriptor table, and there's two types of tables, local and global. We'll talk about that in a sec. But the descriptor contains the following information. The segment space address Base address equals starting address, guys. Okay? It also contains the segment's limit. The limit is the highest value that the offset register can be. That's the limit. It's the limit for the offset register. Okay? Do you see, everyone? This basically specifies the size of the segment. Okay? Okay? So when you compile your code, right, you got this wonderful code that does all sorts of wonderful things, right? It has a few methods, right? Hopefully not very many. Okay? Object-oriented code is actually very, just writing assembly is a much better way. Your methods would all go probably, more than likely, the compiler would place them in their own codes in memory land. Okay? Your methods aren't very big, I would hope. I mean, they might be a couple dozen instructions, it might be a couple hundred, but they're not 64K, or usually not. Right. You probably should, yeah. But the compiler then says, okay, this code segment, which has Nick's method, only needs to be, 3F bytes big. Hexadecimal, of course. Okay. Why is it 3F bytes? Because that's all the segment needs to be. Right? So do you see that automatically handles the fixed size problem? Right? The base address is, where it starts. That's the same thing as what the segment register did in real mode. Okay? So the limit is kind of like the size of the block in memory land. It also allowed for, not all the operating used it, but it allowed for access rights. So Nick's code that's running and Eddie's code that's running, Nick can't, in general, can't access anything of Eddie's and vice versa. So now they're protected, okay? More specifically and more common on a personal computer like your laptop, you got Excel running over here, you got Word running over here, and you have your browser over here, right? Each one of those has data segments and code segments that are allocated to that application. Yes, no? Do you want your Excel stuff accessing the browser or being able to access it? Probably not, unless the user specifies, right? But that's how they protect each other. Do you see how that works? Before, we didn't have that. Okay. There's a few other things that there's a few other things that we don't need to. But this is what it did. Now, let's talk about how it works next. You guys go with that? What I can do is I can post the slides. I'll post them on the embedded, and Nick or Brian or somebody, you can copy them to the ACM so everybody can see them. Okay. Because all this information. So segment register is really a segment select. It's a descriptor selector. Okay. How does it do it? Well, here's how it does it. So we have a 16-bit segment register contents. Okay. Okay. Before, again, it was used like this. Not anymore. The least significant two bits specified a priority level. Priority levels were used by the operating system. You know, if there's a really low priority, but something far more important is going on, then it'll take care of the far more important stuff before it gets to the priority. Okay. So this is byte bits 0 and 1. Bit 2, that's the table indicator bit. By the way, everybody, you've all had intro to CSE, right? Yes, no? So you know what a bit is, right? Okay. Yeah. Lesson learned. You don't need to. The department chair basically admitted it, did he not? So table indicator bit 0 means global. What's global? Exactly, but I'm going to rephrase. Anything can access that segment. So it's like system time, right? That's accessible to any application, and it should be. Other stuff that I can't think of, those are global segments. Okay, the information in them is available to everybody. Okay. 1 means local. What does that mean? Field of view? Okay. You're totally on the right track, if not nailed it. A local segment is only accessible to the task that filled in the segment register. So only the application. Nobody else can access. So it'd be stuff that's local only to Excel, or more importantly, only to the particular spreadsheet that you're working on in Excel. Nobody else can access. Okay. Yeah, variables. Yeah, exactly. Yeah, local and global. Okay. There is I mentioned here, descriptor table. There's a local descriptor table set up by the operating system. There's a local descriptor. They are two different things separated in memory. They do not overlap. Okay. The rest, the other 13 bits, bit 15 all the way down to bit 3, if you do the math, that's 13 bits. This is the segment selector. Okay. Do you see that the segment selector says which segment, the table indicator says which table? Those two pieces of information specify exactly where to go to get the descriptor. Do you see that? Those two pieces of information. Okay? So, we got this bad boy, right? And it's going to specify a descriptor. Yeah. Yeah. Yeah, you can kind of think of it that way. Yeah, definitely. Yeah. The descriptor is an 8-byte thing. I don't know what to call it. It's 8 bits big, and the bytes are arranged as follows. And there's some historical context as to why this is. When I first give it to you, you're going to say, "What in the world would you think?" And you'd probably be within your rights to think that, at least at first glance. Zero index, this is byte 0, this is byte 1, byte 2, 3, 4, 5, 6, 7. Okay? The descriptor format is as follows. The descriptor contains the segment's base address. We said that, right? So within this 8-byte structure is the base address. Here's how that base address is laid out. I mentioned earlier that, with the 83, 86, we started to go to 32-bit addressing, right? So all these quantities, you're going to see a recurring theme, 32-bit, 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 32-bit. Okay? So how big's the base address? 32-bit. So the least significant byte the base address LSB is in byte 2. Okay? Don't yell at me. I didn't set this up. I did not lay this out. Do not yell at me. Where do you think that? Do we have a die? 8-sided die? 3. It kind of sort of makes sense. No, 7's used, but not quite yet. So this is bits 0 through 7. Yes, no? Least significant byte in a 32-bit quantity. The next byte is bits 15 through 8. Okay? And again, this is part of the base address. Where do you think the next byte is? We've only got half the base address specified. It's 4. Which bits is this going to be, guys? Very good. Good job, man. Yeah. Yes. Yeah. Do you mean in the segment itself or in the descriptor? We're going to do some example, and it'll be totally. I really hope and pray that you guys, get the hang of it. I'm gonna try to make. Where's the most significant byte of the base address? I kind of already spilled the beans. No, 7. Don't blame me. I'm just a messenger. Don't shoot the messenger, guys.
Better I hand the message.
I think I know why they did this. So I don't think we can be too cross with Intel. Although they certainly deserve a lot of our wrath, I agree. Not as much as Microsoft. I alluded to it earlier, but you might not have picked it up. The 8086, 8186, they were all 16-bit stuff. 20-bit address space, okay? Address bus, okay? One megabyte main memory. They didn't do any virtual memory. They didn't do anything like that. The 286, though, did. They did virtual memory. They also expanded the address space from 1 meg, 20-bit, to 24-bit. Wouldn't these 3 bytes put together make for a 24-bit base address in the 286 structure? Standards last forever. Okay? Start going down a road, right? And stuff gets added down the road, right? Eventually, it's too big to turn back and create a different standard. Think about the metric system. It's been around for 200 years. Do we use it? You might use it in math, physics, sure. Chemistry, sure. You get out in the real world, nope. Go. Yep. That's exactly why it is. They used to jam in the very earliest mechanical typewriter. They used to jam. So, like, they forced the typist to have a little extra finger movement to give the keys time to track. What does our keyboard look like? Identical. We don't have that problem anymore, clearly, but how's it laid out? 99.9% of the keyboards are QWERTY. So yeah, standards last forever. And eventually what you're doing has enough mass that it's really, really hard to turn it around. Okay. So I'm pretty sure that this came about based on the 286. And when the 386 and forward came out, they had to come up with another byte, right? For a 32-bit address bus. Well, they couldn't just slap it into the next location because in the 286, this was the access byte. It was an 8-bit access that protected segments from being accessed by stuff that wasn't allowed to access it. Okay. When you got so much written and developed for that protocol, you're talking millions of engineering hours. You want to flush that down the drain? That'd be a pretty hard sell. Go, Jacob. Absolutely. Yeah, I'm really glad you mentioned that. That is an excellent. Intel to this day has maintained backwards compatibility. Okay, Microsoft hasn't, but the hardware has. Okay, so if you can get an operating system to run your 40-year-old programs, and I probably still have a few that I wrote way, way, way back in the day. But if you can get an operating system to run them or write your own, they'll run on the modern hardware without a problem. Not true of Microsoft. Nope. Yeah, backwards compatibility has been valued by the hardware. How many times you upgrade some, like a version of something? I don't know. Office products have been good, but no, Brian, they haven't. Oh yeah.
all we want to do. Yeah. Like, better.
Okay. Now, we'll talk about the granularity bit in a moment. The descriptor also contains the limit, right? We talked about the access rights, we talked about the base address. It contains a limit too, specifies the size. The limit is a 20-bit value, and we don't have a lot left, do we? So the limit bits 19 through 16, these 4 bits, reside there. The rest of the limit is down here. Yes, at one time they did. I'm going to explain it. No, the granularity, this is bits 15 through 8, and this is 7 through 0, right, guys? Okay. So what's up with the granularity bit? Well, the granularity bit, there we go. It's on my. So, the limit's 20-bit, right? 20-bit. So if that's the limit of the offset register, what that means is that our segment size is fixed at 1 megabyte, right? That's the biggest. Well, what if we've got a system, and there are some out there, used by maybe chemists or astronomers or something like that, that uses numbers that are incredibly big and or incredibly small, right? 10 to the plus something, where there's something big, or 10 to the minus something, again, where there's something, right? So they gave us a granularity bit where it specifies the size. I'm sorry, but let's call it the limit. Keep the limit is in bytes. So this would be for 1 megabyte maximum size, right, guys? For a segment. Or, and I'm writing it this way because I can't remember if zeros is 1, 0 value is 1, 1 value is the other, and I can't remember what. Or it's in 4 gig. So this would be the limit is in 4 kilobytes. Okay, so if your limit was 2, it'd be an 8 kilobyte segment. See that? Where if the granularity bit's a 1, or if it's in bytes, I should say. If it's in bytes, if the limit's 2, then 2-byte segment. So again, they tried to make it as flexible as possible for this. Did the light turn on? There's a trade-off with this, right? By the way. Go, Nick. It says both. Well, the lower bound is always 0. But if it's one value, let's say, yes, right? Four kilobytes. Then your maximum is the entire RAM. Go, Jacob. Yes, yes. Mm-hmm. Yeah. It's kind of like if you're making a recipe, right? The unit of measure could be size, right? It could be in ounces or it could be in gallons. You better get it right. Yeah. Yes. Yeah. Okay. Now, do you see the trade-off though? There's a huge trade-off. How about number of segments? If your maximum size is 4 gigabytes, you probably aren't going to be using a whole lot of segments, right? You know? So you fire up your little Minecraft or solitaire game, right? Right? Yeah. You're not going to be able to do that along with all your high-tech stuff because you're going to run out of memory space. Okay? Mm-hmm. Yep. The default is 4K. I'm sorry, not 4K. The default is bytes. Okay, because most applications don't have any data structure, be it code, be it stack, be it data, that's more than a megabyte. Think about it, right? I mean, yeah, the overall size can be much larger, but it can be segment. I mean, how many arrays are more than how many arrays? I mean, it's possible, but in practicality, most of them are. Yeah, but we have more segments to deal with that. Um, well, we've been going for an hour. How much you guys want to dive into paging and how deep do you want to dive? Well, I don't want to bore any. Processing power really doesn't enter into it. Read-write memory. Understood. Understood. That's why you're here. Oh. Yeah. And it deals, both the limit and the granularity bit play into that. Now, this is an operating system thing, guys. Okay, this is an operating system. So again, if you have the granularity bit set to four kilobyte chunks, that size goes for everything. And as far as I know, you can't change them on the fly. Okay, you might have a dual boot. Okay, do you want to see how segments would get selected? Because I can bring up my go. Notepad.
So granted, Google Chrome is terrible at it. It's pretty stacked. The amount of stores. Yeah, so you don't have like a billionaire come in and buy out like all the stores a lot. Several other. You pretty much tell you like, whoa, you had enough of all kind of. Oh. Really?
I'm trying to get that here. So I turned that screen on. Here it is. Yeah, it was showing there, but it wasn't showing up on the board. Yeah. 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 They all use something similar. I'm not. ARM doesn't use segment. So when Nick, you've had who's had embedded? Did you guys talk about memory and embedded, Jacob? Okay. Did I have you for that? Okay. What's that? Oh, yeah. Yeah. No offense, Jacob. I felt like we were always playing catch up because the main campus guys didn't know it. Did you get that impression? There were a couple of really good ones. There were. But most of them, they just didn't have the foundation under one. A lot of them didn't care. Okay. What's that? Just here. What I prefer. Okay. The two descriptor table registers are the local and the global. We already said that, did we not? Right? How is it determined? Table indicator bit. Right? So, how do we pinpoint where a descriptor is? Okay. I sure try. Okay, so if we want to know if the data segment register contains this and the extra segment register contains this, right? If we wanted to know what descriptors these segment register values were pointing to, we have to break them up, remember? I erased it. We have to break them up into their, grab the first 13 bits, right? And we also have to look at the table indicator bit, right? So, breaking this up, you guys have had hex. You guys freshmen? Okay. When you have digital logic and forward, you'll understand my remark about the hexadecimal addressing system post office. So, data segment in binary, direct conversion, right, guys? Not a lot of thought involved. Yes, no? If you haven't used it for a while, sure, but it would come back to you in about 10 minutes. Each nibble has a 1-to-1 correspondence, right? Each 4-bit binary pattern has a 1-to-1 correspondence with the nibble up here, right? So 8 is 1000, C is 1100, 1 is 0001, 7 is 011. You should have had that, right? No? Really? Mm. You did. Yeah, so you didn't have it in 1030, Eddie? Okay. Well, that's a nibble, okay? A 4-bit value is a nibble, okay? So hexadecimal is nibbles, okay? So we break this up. We really don't care about priority, right? If we're just worried about location, right? What's the table indicator bit? So 1, local or global. We could do this democratically. Who says local? Shout it out. It's local. Global 0. Okay? So it's in the local descriptor table, right? And then we take these 13 bits to identify a descriptor number. In hex, what's the descriptor number? Everything's in hex, guys. Well, you start here and you work to the left. Remember that, guys? First nibble is, what's the next one? Next one. Right? We have the 1 up front. Okay? That's the descriptor number. Okay? So what's the offset? The descriptor number, the offset in the table, what's an offset again, guys? It's kind of a displacement from the base address. It's the distance from the base address, right? Not how far you need to go, it's how far you need to go for the access, right? Right? So like when we had our memory land analogy, right? So the base address is the house on the corner, and that's offset 0. If your offset is 3, you're going to go 1, 2, 3 houses from the one on the corner. Yeah. Yep. So the offset is the descriptor times 8 base 10 or 8 hex. So you multiply that by 8, right? Okay, to get the offset in the table. How do we multiply by 8? Take that value. How do you multiply by 1,000 in decimal? You add 3 zeros to the binary value, not the hex value, the binary value. Okay? Well, we have the binary value up here, don't we? So we have the most significant 13 bits, and we chopped off the least significant 3, did we not? To get the number? Well, do you see that we just take this number? It's the segment register contents. Bits, what, 15 through 3? 000 binary appended to them, right? Just replace these bad boys with zeros, and that is your offset. Oh, it is? It didn't update? It's updating, isn't it? Oh, duh. I will do so. Bad. Sorry. Change windows, camera. How's that? How about that? Is showing there? Thank you, Eddie. Thank you. So, guys, for this, the offset equals, start with what we had, 8C17, right? Well, what's the 7? 0, 1, 1, 1, right? Right? Well, we said we're going to clobber those least significant 3 bits. Yes, no? So the 7 becomes a, good job. That's the offset in the table. Okay? So if we have the offset, don't we need the base address? In other words, where does the table start? Right? Well, which table, local or global? Local, right? Well, if you look way up there, we have the local descriptor table base address, do we not? So our so the offset we already determined is hex 8C10. It's in the local descriptor table, right? The base address is what for the local? Do you see that? We add the 8C17, or I'm sorry, 10, right? Now, if the gods are smiling upon us, we will have this value in the table. I think it's right here. And how big is the descriptor again, guys? Remember? 8 bytes. The way I arranged this table, each one of these entries is 4 bytes, okay? Contents are 4 bytes. The address is here. Notice that the address is increased by 4 at a time, right? That's because each entry is 4 bytes, okay? So the byte at 9FCA 8BEC is 70. So ED is 92. EE is 00. EF, say, that's how the, okay, and it's common to see it arranged, right? So if I outline our descriptor, wouldn't I outline this? Yes, no? Did I do that right? 9F, CA, 8C10. That's here. So it's these 4 bytes, but remember the descriptor is 8 byte, right? See that, Nick? This is the descriptor table, so each entry is 8 bytes. No matter what. 8 bytes, okay? It's starting here. 1B is the least significant byte. 6A is the most significant. Okay? Do you see that? Everyone good? So we can shove these 8 bytes into our table, can we not? Our little mapping, right? Want to do that? Here we go. Yes, but I would modify your statement, say these 2, not addresses, but entries, because it's 4 addresses in each, because it's 4 bytes. So byte 0, 1, 2, 3, 4, 5, 6, 7, okay? What's the limit, guys? Well, here, time out. Okay, cool, great. That's awesome. Oh, that wouldn't make sense to you at all.
Oh.
That's not right. No. Does everyone see the mapping from here to here? Everybody understand that? 7. You got it? Make sense? Yeah. So remember the limit, right? Right? So we concatenate 0, right, with the bottom row. In this example, this is our limit. Hexadecimal. It's the maximum value, the offset register can. So the size is not 1B. Do you see it's 1B plus 1? Because it's 0 index. So 1B plus 1 is 1C, which is 24 decimal. No, 28 decimal. 16 and 12, 28. Yep, 28 decimal. 28 bytes. Okay? What's the base address, guys? we take, I want to pick a different color. This guy, right? Then what? These two, right? Is that a B8? Can't read my own writing. You guys that haven't had me before. That fully defines our segment, gentlemen. Fully defines it. And it just so happens, maybe, wrong mouse. Is that visible in 6A, 8E? Yep. I have to. Where is that segment in this mesobyte? Right here, right? This is the beginning byte in the segment, guys. This is the base address. This is the byte at the base address. Yes, now? See that? How far up? Well, this is offset 3, offset 7, offset B, offset F, 1, 3, 1, 7. What's the offset? 1B. So it ends here. So we should have 7 rows, each containing 4 bytes. Yes, no? That's our segment, guys. That's the limit. If we had 0 plus 1B to that value, we're going to get 6A, 80, 7F, D, 3. Yeah. We'd be going way up there. It wouldn't be 28 bytes, it'd be 28 times 4K. Okay? Question. So, do you want to do paging and absolutely. We're not doing it just. Not at all. Okay. All right. So, we'll do one more thing. How's that? We'll do one more thing, not to mention the fact in the thing that is posted, there's got to be a bug in because it's not working out. The only way it guaranteed to work out is if I had a 4 megabyte like memory table. But yeah, I'm sorry, 4 gigabyte. Anyway, yeah, I didn't think you guys just a lot. So, guys, I'm going to leave this with you. I'm going to, one more thing. Move, bx equals, we'll say 0, 3. No, 4. Yeah, 4. Move ax colon dx ds I'll be explicit, DS:, EX. Now, for those of you that have not had, and probably half of you, that have not had computer architecture, MOV is move. Now it's in both the ARM architectures and the Intel architectures, and probably MIPS as well. Move really should be copied, right? We're not moving data, we are copying. Okay, we're not physically moving the bytes from here to here and leaving the source, vacant. We're not doing that. Copy. Anyway.
You know what? Let's mess up higher protocol. Screw tradition. Let's change move to copy, see what happens.
Or worse yet, what if they said, you know what? We've been rewriting the meaning of the word move, so let's make it do what it really means.
Oh, good God.
And vacate. That'd be horrible, would it not?
No Apple product. You know what? That would.
Nothing in your car would work because it's all ARM. Your Keurig wouldn't work, for God's sake. Yeah, you definitely want to say, no, I'll keep my old version. Okay, so this is a move, guys. This is the source. This identifies where the data is that we want to copy from, okay? No. This is segment register, offset register. It's not a concatenation. The colon means several things. Yeah, I know what you're. This means it's in this segment. We're using this segment register and this offset. Okay. Well, direct addressing. Yep. And we're going to copy the contents here in memory land to here. Okay. Right. AX is 2 bytes. AX is 2 bytes, so we're going to move 2 bytes, not 1, not 4, 2. Okay? When you have computer architecture, all this stuff will totally make sense. Well, we know with the data segment being set to this address, we know where the segment is, don't we? Right? So where in the data segment are we going to, in the segment, which bytes are we going to pick on? Well, we have the base address that's right here. We also have, as I mentioned before, the offset. So we add 4 to that base address. Okay? 0, 1, 2, or 0, 1, 2, 3, 4. So we move this byte, right? Okay? So the address that we're going to pick on is what? 0x6a, yes, no? 8e, yes, no? Keep on going. I get BC. Yeah, because it's offset 4. Okay? Now, 2 things. How many bytes are located at this address? 1. 1 byte. It's 1 byte per address. We have to move how many? 2. Because we're moving into AX. 2 byte, right? So the way the Intel architecture and almost every other architecture, the only time I've ever seen a difference is in communication. Okay, communication system. Okay? If you're moving more than 1 byte, you start with the byte that's specified at the address specified, and then you go up in count to grab the next bytes that you. So we're not going to move just the 98, we're going to move that. The low byte, that's called little endian. Okay? So AX is going to contain what? Yep, in that order. Yep. Yep. Even back in the 886 days, you can move 2 bytes at a. Okay? So the result of this instruction is that AX will contain FF98. I don't know what it is. No clue. Okay? Just as importantly, this is all a lie. Okay? It says, you're familiar with me lying to you, Jacob. Come on, dude. A little bit. A little bit. This is what's called the linear address. Have you heard that term? The linear address space does not equal main memory physical address. Okay? All right? Don't. To whet your appetite for the next one, will be the last thing we talk this evening. And it's been suggested by previous classes meaning, class of 2003, class of 2000, by previous classes, that all of your ACM t-shirts should have this on the back. Because it's incredibly cool. The way the Intel, let me lower the way the Intel systems work, and you got to remember every personal computer uses some kind of an Intel processor. Oh, mine's an AMD. Well, AMD is based on the Intel protocol. Unless you got an Apple. But even Apple uses Intel processor. That's been true for like 50. Which one is? Are they? ARM's pretty cool. So, guys, your program generates what's called the logical segment register and offset. Okay? That goes through, as we've seen, that goes through the segment selector to specify where to go in the table to get the base address and size and all that kind of stuff, limit. So it goes in the either the global or local descriptor table, grabs the descriptor, right? The descriptor points to a area in memory. The offset is added to that area and forms what's called the linear address. Okay? Now, the first table that I gave you, and we outlined this, right? This. The contents here are in what's called the linear address space. It is not what's in main memory. This is something we can conceptualize, something we can picture it as. It's not physically what it is. Physically, and this is, even ARM does this, uses the linear address, breaks it up, and we'll talk about this next time, breaks it up into 3 parts, possibly 2 parts if it does something a little different. A page directory specifies a page directory entry, which points to a page table. The table bits specify a page table entry, which finally gets us to physical address. It is. And what if this page is out there on the hard drive? Processor can't read stuff from the hard drive, not directly. It has to be brought into memory land. It's called a page. That's called a page exception, also known as page fault. Okay? All right? Again, it's, remember interrupts? It's not a big nasty, right? It just means something happened, and we got to interrupt the flow of things to service that event. Okay? It's not a big nasty. That's up to the memory system. It's all in the memory system and the memory drivers and all that go along for the ride. Yeah. Yep. Yep. And it's all transparent to us, isn't there? Isn't it? It's all transparent to us. Okay? That's all the stuff inside the operating thing. But it's doing a whole lot of stuff that we don't even pay any attention to. And the vast majority of users, no clue that it is. Right? My wife certainly doesn't. She'd be like, what's memory? Well, pretty loaded question, isn't it? Okay, we'll pick it up here whenever you want me to come back. I don't, if you gave me a date, I probably would give you a very firm maybe. That's before this. Aren't most guys still going to be out and about doing stuff? I don't know. I'm aware. Yeah, I will be available, yes. I'd rather meet her. Wouldn't that? Have a pizza night. When do classes? Okay. I'd count on 2 weeks. Yeah, something like that. Wouldn't that work better? Just have a pizza night. 6th. What's that? It's up to you guys. I'll probably be at home. Doing what? I don't know, but I'm sure my wife will be doing something. All right. That's it for the day. I certainly hope it was interesting. And we'll pick it up here and take it all the way through the paging system. We'll trace it from your program all the way down to the physical byte in memory lane. All right? Yeah. Yep. I'm going to kill the projector, Nick. No, is that okay? Yeah. Right. Right. Okay. Good. Good. As fresh found the front. Thank you. Saw that. That was like foreman. Glad time out of their busy schedule. Watching a mass. Professor Nowlin, thank you again. As always, please
keep an eye out for future events, doing stuff like we're gonna have after Christmas. You guys love your family. I hope so. So you're gonna probably be holidays with them. We want to keep nice and out. So, anyways, thank you again for everyone for coming, and I'm gonna end the recording. So again.
Thanks, guys.